welcome. Thank you for joining us for the excellent June Rhodes C++ workshop. It's going to be a wonderful day. I've had the privilege of being able to get a preview of some of the slides of some of the material that's going to be delivered today. And yeah, it's going to be a good one. So glad y'all can join us. I'll bring June onto the stage now and yeah, hand over to her.
Hello, hello.
Hey, June.
Hi, everyone.
Yeah. Oh, sorry, I'll just jump off. Awkwardly
Yeah.
remove myself, and just it's all you.
All right, thank you. All right, hi, everyone, and welcome to the Unreal Engine C++ workshop I'm going to be running all day. Before we begin, I'd like to acknowledge that this workshop is being given on the traditional lands of the Bunurong people, and I would like to pay my respects to their elders, both past and present, and elders from other communities who may be here today. I would also like to invite you to take a moment to think about whose lands you are on. Sovereignty was never ceded, and this always was and always will be Aboriginal land. Before we get into it, just a few housekeeping things to give you an idea of how today's going to run. So if you've looked at the schedule, you will notice that there is 10 or 11 workshops all up today. The first three are going to be very foundational C++. So I've got like lots of slides. I'm going to be going through them. We'll take questions towards the end. Yes. I'm going to be taking questions towards the end of those. And then once we get into everything to do with text onwards, it's going to be much more conversational. I've got a few dot points I want to go through in terms of like things I want to cover, but then it was sort of more your opportunity to sort of be like, hey, what about this? What about that? And we'll go and investigate things that seem interesting. So I am going to get started because we have a lot to get through. So we're going to kick it off with, oh yeah, the other thing before I get started, some of the stuff might seem, this is quite dense material, so some of it might seem a little overwhelming, but I do ask that you stick with it because some stuff I cover for completeness or to go in depth. Please don't feel like, oh, I didn't understand this one thing or one topic or one slide early on in like workshop number 3. I won't understand anything later. No, it's totally fine. Things get higher level as we go on. So yeah, stick with it. It'd be great. Right, so translation units and the preprocessor. Let me bring up my little notes here. All right, so this is the fundamental how does C++ compilation work session. C++ compiles very differently to most other modern programming languages that you might be used to. And if you don't understand how things are compiled, you're going to get confused very quickly. So what we're going to do is we're going to look at how C++ compiles. We're going to look at how that compares with C#. And everything that kind of goes on under the hood when your like C++ programs being compiled. The idea is that you understand the path that your code takes from the editor to the compiled binary that you get on disk. So if we look at how C# compiles, what happens is when you compile a C# assembly or C# project, the C# compiler gets every single file passed in as an argument. So it's aware of the entire program. It reads all the files. It is able to parse everything up front. And because it does this, it can know that in this example here, it can know that blah is a class, right? And it knows what the contents of blah is and what functions it has available. C++ does not compile this way. It does not compile everything all at once. It compiles one file at a time. And each file is a translation unit. So if you see the term translation unit used, or if I say the word translation unit, it means a single C++ file is a translation unit. Why does it work like this? First of all, we have to go 50 years in the past to 1972, when the programming language C was being first written. And to understand the context in which C was written, which C++ is the evolution of C, we sort of have to kind of look at what computers looked like back then and sort of try to rationalize what decisions were made as to why things work the way they do. It turns out it's quite difficult to find a rationale for some of these decisions made 50 years ago. So some of this is going to be me making a reasonable guess as to why it is this way. The stuff I could find is from the development of the C language paper, which they wrote, which some of the original authors of C wrote in 1993. And even they say that they don't really remember why some things were done in a particular way. So, I'm kind of I'm kind of working with what I've got here. To give you an idea of like the constraints that we're working with in this time, C was originally developed on the PDP-7. Now, this is a machine that has 8 kilobytes of memory. And if you can imagine trying to fit anything in 8 kilobytes of memory these days, that's pretty tough. And now try and put yourself in the mindset of you have to fit your operating system, like all the user space programs, the compiler, and then the compiler has to actually run and do the work. That's extremely memory constrained. That's an extremely memory constrained environment. And then the PDP-11, which it was ported to, I think, a few years later, only had 24 kilobytes of memory. So again, extremely memory constrained environments. And if we look at what a compiler needs to do, it's actually quite a lot of work. So first of all, it's got to read files in, so it's got to read the actual text in the file. And then what it's going to do is it's going to lex or tokenize that text. So for example, let's say we have a text file, or we've got a C++ file, and it's got like a string literal in it, right? Between two string quotes. That's going to form one token that is just a string literal token. And then you might have, I don't know, like the plus symbol, which would become like the plus token. The parentheses would become the parentheses token. And we do this because it makes the next step easier to work with, which is the parsing step. And the parsing step is responsible for taking that linear set of tokens. So now we've handled all the things like if you've got a string literal and you've got like the backslash for escape codes and stuff like that in it, you would resolve what the escape codes resolve to in the lexing step. So then we're basically going to parse all of this linear set of tokens, and we're going to turn it into an abstract syntax tree. And that's because we're starting with a linear set of tokens. Like you might have the if token, for example, and then you've got open parentheses, a bunch of tokens for expressions, an open brace, and then you've got a for token, right? That on its own is not particularly useful for emitting machine code. So we're going to turn it into a tree. It's called an abstract syntax tree. And so then we will know conceptually that the for loop is within the if loop. All right. Then after we've done that, we've got to do type resolution, or in C++ case, this is sort of mixed together because of the way C++ types work. And then, so we do type resolution, and then we emit machine code. And as you can see, this is quite a lot of work for the compiler to be doing. And in these memory constrained environments, if you had all the source code for your entire program in one file and you try and do this all at once, you've got a problem, which is that even though your resulting executable might work within the memory limitations you've got, you don't have enough memory to compile the whole program at once, because you just don't have enough memory. So what we do is we're going to split up the work, and we're going to actually split up our program. We're going to split up our program into individual files. We're not going to do that just because it will make organizing things easier. We're going to do that because if we don't, we can't compile. We literally just can't compile stuff. So what we're going to do is we're going to compile our individual C files into object files. So we're still going to do all that work with reading a file. Excuse me a second. We're going to tokenize things. We're going to parse things. Going to go through our abstract syntax tree, type resolution, and then we're going to emit the machine code for the functions that we've written. And now we only need enough memory for the compiler to compile each C file or each chunk of the program in sequence. And then at the end, we're going to take all of the machine code that we've outputted to these object files, and we're going to stitch it all together, and then all the placeholder function pointers, which I'll talk about in a moment, we're going to swap them out for the actual function locations that the linker now knows where they are because it's stitching everything together, and emit the resulting executable. And so this, just to compare again with C#, works quite differently, right? When the C++ compiler runs, it doesn't know what's in all of your other C++ files. All it has when it's running is literally the file that you've passed it. And it will then compile the object, and then later on, that object will go into the linker. But then that sort of raises the question, how do we reference things across files, right? Like, if the C++ compiler is compiling one file at a time, how does it know what functions and what types are available in other files? And the answer is forward declarations, which is basically a way of us saying this type or this function, it will be available when linking, right? And this is what it looks like. But we're not going to give you the hard job of actually parsing the implementation of this function or the implementation of this class just yet. We're just going to tell you what it looks like so you know the type information so that you can actually reference it in the code that you are going to be compiling. And when the C++ compiler runs, obviously, okay, it knows what square looks like, right, when we're doing this forward declaration. But it doesn't know where square is, right? It's not compiling square. It's not emitting the code for square. So it leaves it as a placeholder. It just leaves it as a bunch of zeros with the expectation that the linker will fill it in later when it has all the object files. And so we can look at this comparison here where on the left-hand side, we've basically got, on the left-hand side, we've got both functions in one. The compiler obviously knows the address of square. So it's like, okay, cool. I'm going to put square at this location in the executable. I'm going to put main at this location, the executable, and therefore I can reference it back up. When it's compiling with a forward declaration, it doesn't know where that is. So what it does is it basically just says, okay, I'm going to leave it blank. And then in the object file, which is not an executable on its own, it's like, hey, linker, I need you to fill in this location. This location needs to be filled in with a function that has this particular signature. And so we can see the linker doing this here. So on the left-hand side, we've got the square. I'm going to get to that in a moment. We've got the square object file, which has the implementation of square. We've got the main object file, which has our main function. It has that, you can see that the 000 there, that's still placeholder. And then the linker is going to stitch this together. So you can see it's basically stuck the square function in and the main function in. And now you can see the linker has replaced that call with the actual location of square that the linker has placed it in. Cool. Now we can reference things across. Now we can compile our programs in chunks and get a resulting executable, and we don't have to compile the whole thing at once. And we can do it on our extremely memory-constrained hardware. Important to note that this is why if you forward declare something, but then you don't actually get it, the C++ compiler will be like, totally fine. It doesn't care. It's like, sure, you've told me you're going to have this thing available later. And then when the linker comes along, it's like, I don't know where that is. But the thing is, the linker doesn't have the context of your source code. Remember, it's only getting these object files. So when it's being told, hey, I need you to fill in underscore Z6 square I, the only thing it can give you in the error list is, hey, underscore Z6 square I is undefined. And you probably look at that and be like, I don't know what that is. And it's especially, it gets even worse when you've got like classes and like long namespaces and stuff, because you get really cryptic. You can get really cryptic error messages from the linker being like, hey, this thing's undefined. And it's because the linker doesn't have the original source code. All it's got is basically, hey, you've told me this thing will be available, and you know your nice, well-named C++ function is going to be called this really mangled thing at the linker stage, but it's not actually there. I can't actually build the program because I don't have the location to fill into the final program. Yeah, I'll mention this here as well. The linker is also, the linker is also the part where library references get linked in. So like if you're linking against a third-party library and you don't link against the library properly, but you've included like the header files, which I'll talk about headers in a moment. That's why you get all the linker errors being like, hey, all these library functions don't exist because you haven't linked properly against the library that actually provides the functions and all the call sites. So that's great. We can compile in chunks now. What do we do when lots of C++ files need to forward declare the same function, right? Sure, we could put our square, like we could literally put int square int n in like the 100 C++ files that need to know about it. But that's really impractical because you can imagine that if you want to add a parameter to square, suddenly you now have to go and update all of those files. So instead, we have this thing called a preprocessor. And the preprocessor basically takes your code before it's passed the C++ compiler, and then it expands out all of these includes and all of these defines, all of these preprocessor directives, and then it passes the result to the actual compiler. And I really want to stress that this is a literal text include. It's nothing fancy. You can technically run the preprocessor on non-C++ code, and it's like, sure, because again, it's just a literal text preprocessor. You don't even have to produce valid syntax. That's why if you define macros and stuff, and the macros just end up resulting in like not syntactically valid, the C++ compiler will be like, what does this mean? This isn't valid, but you might get a cryptic error being like, hey, it's like here, and then you look at it and it's like a macro, and you're wondering like, why is this happening? It's because it's just expanding. So what does the preprocessor pass to the compiler? So on the left, we have a very simple 4-line program. We are including the standard IO header for C, and we are calling printf to print something out to the console. And that expands to 551 lines of code that the compiler actually parses and compiles. So when you compile the program on the file on the left, the C++ compiler is actually compiling the thing on the right. And you can see we get all of these. We've got all of these directives. So you'll notice all these like hash 461 user. It's a bit obscured. Unsurprisingly, I actually ran out of space on this slide to put all of the source code. These little like pragma directives up here, these are actually what allows the C++ compiler to say, hey, this syntax error is in this file at this location. Because you can imagine that if you expand out all of the includes and you have an error in, say, deep inside the headers somewhere, the C++ compiler needs a way of saying, oh, the error's in this header, right? If it just got the expanded content without all of these line directives, it would have no idea what file the thing was actually originally from. And then so interspersed with all of these line directives, it's telling the C++ compiler the actual locations of things. You then have all of these type defs and all of these function definitions, and this is all just straight from the standard IO header. And you can see that the one function that we're actually using, printf, is highlighted in yellow here. And then we can see at the very bottom, we've got three lines of our actual program. I want you to take a moment and think about how many lines of code the Unreal Engine headers expand out to. The answer is, it's a lot. It can be a lot of code that the C++ compiler ends up actually parsing and compiling. This is also why, if you've ever done stuff in C++ before and you've left the semicolon out of the end of one of the, like, let's say you've got a class defined in a header, right? And you forget the semicolon after the class definition, and you might get a C++ compiler error inside the file that's consuming the header, and that's because synaptically the error is to not have terminated the previous structural class definition before you start something else. But the error location will appear in your file because the C++ compiler is just getting the whole thing. It's not compiling these things individually and being like, oh, that's the end of a header, you should have finished it off, because it's just all text. Wow, this seems like a lot of redundant effort. Imagine that lots of files are all including the same headers, right? And every C++ file you compile has to parse all of that header code every time from the actual text. This is really slow and redundant, right? Especially imagine like in Unreal's case, like you could be easily parsing hundreds of thousands of lines of headers for maybe an actor class that has no more than, I don't know, a couple hundreds of lines. So you can imagine how much it explodes, right? Doing this every time for every C++ file is slow and redundant. And so there's a solution for that. It's called precompiled headers. And the idea is that you run the compiler in a special mode that is just responsible for compiling the headers. And it compiles the headers not to an object file with machine code, because headers are just about the declarations and the type definitions. There's no actual machine code to actually compile to. But into a special binary format that the compiler can load instead of parsing the text. It's probably like a serialized version of the abstract syntax tree we were talking about before, and like all the type definitions. It's probably going to vary between compilers. And then when you've compiled your precompiled header, you precompile, you build the precompiled header first, and then every compiler invocation after that for all the C++ files you're compiling, it just loads the serialized, like the more optimized binary format of the precompiled header instead of reparsing all of that, all of those common headers. And that speeds up compilation because we're not basically doing work again that we don't need to do. Other things the preprocessor does, the preprocessor lets you define macros with like define function, and then these get expanded again. Text preprocessing time, they get expanded before the C++ compiler sees stuff. And macros are very important later on for the uClass and uObject system. We're going to talk about that later. I'm not going to talk about that now because we've got other foundational stuff we need to do first. For now, the important takeaway points for the preprocessor and translation units and how things get compiled is to understand that each C++ file gets compiled on its own. We use forward declarations, so C++ files can know about things that will be compiled in other C++ files and available to the linker when it's building your DLL or executable. We put forward declarations in headers because we don't want to copy and paste them to every single C++ file manually. The compiler actually compiles the fully expanded output from the preprocessor, not just your file. That means that all of the headers and macros are fully expanded before the compiler does any parsing. Think about how the included macro use is expanding in your file, right? If you're getting weird syntax errors that you just like, this doesn't make a lot of sense to me, or like, I'm not missing a semicolon here. Think about how the macros are expanding. And in any reasonable IDE, you can like control click on a macro and go and look at its definition. And that will probably help. And if this way of compiling code seems like hacks upon hacks upon hacks, like we've got precompiled headers to solve the problem that headers have, and headers, because we've got problems with like memory constraints for compiling, you know, we have to use do forward declarations because we can't compile everything all at once. That's because it is. It's 50 years of language evolution, starting with a machine that has 8 kilobytes of memory, and because C++ is backwards compatible, very backwards compatible, and has to be able to compile programs, you know, that are quite old and quite long running in terms of their development cycles, it's very slow to change the way that it works. And that is the last slide. So I will now take questions from Discord. Or Liam, if you want to jump in and
yes, hello June, thank you. That was great. Oh man, I'm learning a lot. Yes, we have a few. It's a good conversation in the Discord. Not a lot of questions because obviously you're being very thorough. It's been very good. Couple here though I got for you from Ben. So .h files are just header files are just fancy forward declarations. Like is that in summary?
You can put you can put anything you want in. You can include anything. It doesn't even have to be a header file, right? I can include another C++ file. Actually, that's a really good segue into a thing that Unreal does. So if you've ever built code in Unreal, you might notice that the compiler seems to be compiling, you know, like module underscore 1 of 2 .cpp and module underscore 2 of 2 .cpp. And this is Unreal making an optimization for you where instead of compiling 400 C++ files, right? It actually stitches all of your C++ files together, knowing that for a lot of the headers you include, they will have there's a directive called pragma once, and that means the header file is only included once. So the compiler will be like, I've already included it. I don't have to read it again. I don't have to bother with it. It's making an optimization saying that, okay, it's faster to run the compiler once over all of these C++ files at once, because you're probably storing your C++ files, so like one file per class, right? Even though the classes might be small. What it does in order to actually batch all of those C++ files together is it actually generates a file in like the intermediate folder that actually does include path to the first C++ file, include path to the second C++ file, and then it passes that generated file to the compiler. And so then all of your C++ files expand out, and then they expand out with all the headers and so on and so forth. So yeah, you can pass anything you want into the include directive. It doesn't have to be forward declarations. It can be any type of code. Yeah.
Oh, that's great. No, thank you, June. Your font of knowledge is just wonderful. Yeah, sorry, just on like optimizations. So we have a question from Guru here. So the precompiled header files, they're compiled ahead of time, and then they're just included with everything like normal. Like you say, it's just basically like a literal copy paste into the process.
So I'm gonna have to remember off the top of my head. It's fine. So I know basically what happens is when you're compiling Unreal C++ code, it will be like, okay, I'm going to compile the precompiled headers for this module. I think if you're using like an installed engine build from the launcher, it might already come precompiled. But if you're using a source version of the engine, it will actually be like, okay, the first thing I have to do before compiling any code is compile the precompiled headers. And then what happens, I think what happens is when the compiler sees the include for the header file that you've precompiled for, normally you'll make a header file like pch.h, and then that will just have include for all the other headers that you want to precompile. And then when your C++ file includes this pch.h file, the compiler goes, oh, I don't actually need to load that file and parse it. I know from the command line parameters that have been passed in, that's the precompiled header. Instead of going into it, I'm just going to load the syntax tree from the
I could just do a straight load at that point.
Yeah, and then it just like loads straight in and you're done.
Yeah, awesome.
Yeah.
Okay, well that's great. Yeah, thank you, June. Sorry, that's all the questions that we have for that part. Because, like I say, we were moving quick, and there was some great discussion in the chat. And yeah. Oh, actually, someone's just pinged me right here. Sorry, June, while I still got you. So Ben again said, you mentioned that Unreal merges a bunch of your C++ files into modules for efficiency. Does it do anything to take into account how much memory it would take to compile those merged modules? And you mentioned that originally the files were split up for memory constraints back in the 70s. Is that no longer an issue now that we have gigabytes of memory?
Okay, so the first question, I just really want to clarify, I shouldn't have used the term modules because they mean something else, and people are gonna get confused if I stick with modules.
Yes.
I will say batches. I will say batches of C++ files. I don't know the heuristics that Unreal uses to determine what or how to batch those. I would take a guess, and I would say it probably just counts lines of code. Like it's just like, oh, this file is 500 lines long, this file is 20 lines long, and it just like tries to batch that way. I would say that's probably what it's doing. The irony being, with the second question about like, now that we've got gigs of memory, is it no longer a problem? The irony is that because we've got all this header expansion and because we're compiling like code in this way, it still is a problem, because now instead of just like, doing things the sensible way like C# does, now we have to expand 100,000 lines of header files just to compile our 20-line actor file. And so, like, now we've got the other problem of like, it's kind of like, yeah, it is still a problem.
Yeah,
I
sorry, I
think,
forget the term where it's like things expand to fill expand to fill the space, the
yeah,
capacity space. Like,
I think if you look at the heuristics that Unreal Engine 5 has for C++ compiling, it basically assumes that every C++ batch that it's going to do will take up 1.5 gigs of memory on your machine, right? So it will actually, even if you've got 24 cores, if you don't have 24 times 1.5, it actually won't try and compile that many files because
oh,
it knows that you're probably going to run out of memory and you're going to start swapping and then you're going to have disk performance
mm.
issues.
Uh, yeah. Sorry,
I just
one,
realized it's
one more
11
question.
a.m.
Yeah,
Oh,
no, sorry,
yeah,
yeah,
one more
no.
question. One more question. We're
I
good.
just
We're
want
good.
to make sure you could get your break. Yeah, because you're doing great so far. We've got a big day ahead of us.
Oh, that's
From
right. We have afternoon tea after this, don't we? Oh,
Yeah,
cool.
so
We don't.
we have an
Yes.
afternoon tea after this, and then so half a cheeky little break. Sorry,
All
from
right.
Zui. I don't know if I pronounced that correctly. I apologize. Any tips on speeding up C++ compilation times? They say for their game code they use a binary version of the editor. Not really sure what that means. Any thoughts on that one? Maybe
Get more CPU cores.
get better
uh,
hardware.
yeah. Yeah. It's pretty tricky. I don't have anything that's going to be like. I don't have any tips that are going to be like instant wins. Because a lot of what Epic does is already trying to optimize for this, right? They're already doing things like confusing. You remember how I talked about those batches before?
Mm-mm.
Confusingly, they're called Unity builds. And when I say Unity builds, I don't mean Unity the game engine. But they're already using techniques like this to try and optimize the compilation process. So there's no quick wins.
Yeah.
One thing I will say that can probably help is that if you are more specific in what headers you include in files, so rather than including like the generic headers that might include lots of other headers, find out which files actually declare the types that you're using and include those directly, and then that will make sure that you're not
Over.
including like code that you don't
Mm.
actually not actually needing.
Mm.
That's probably the only tip that I really have in that sense.
Okay, so like not better housekeeping, like just try and keep it
Yeah.
clean.
Oh, and I think someone in the chat just mentioned like this fast build and credit build. Those help if you've got multiple computers and you want to if you've got like 3 or 4 development machines, you can then distribute the build over those 3 or 4 development machines, so you can take advantage of all the cores you have available.
Oh, great.
But some of those cost money, so it's a
Yeah.
trade-off as to whether or not it's a trade-off of whether or not you're gonna invest in that or just like get better hardware specs.
Yeah, so follow some clean coding principles, but don't have it redundant includes, or just buy 10 computers. So that's the
Buy 10 computers, yeah, exactly.
link them all together. Yeah.
Yeah.
Okay, that's great. Well, thank you very much, June. So we're going to go on break now, and yeah, I'll chuck up the stuff for the next session. I can't wait to get into that.